So, just a little bit of calculus. We are trying to maximize for a given value of r between 0 and 1, the function f of x given by x to the power r times 1 minus x to the power 1 minus r. On the right-hand side, you observe that we really have the product of two functions, a function x to the power r, let's call that g of x temporarily, and a function 1 minus x to the power 1 minus r, let's call that h of x. So f of x is a product of two functions, g of x and h of x. I want to maximize f. Elementary calculus tells us that to maximize a function, I take its derivative and find where the slope is 0. Right? And that's where the cusp of the function is. How do you take a derivative? Well, I'm going to have to take a derivative of the functions g and h. But each of these functions is of the form of a power. And I know exactly what an elementary differentiation of a power is. So we start with a formula for the derivative of a power and apply with that the chain rule for differentiation. The derivative of a product g times h is g prime h plus gh prime. And that is all we'll need. Then all is over, bother shouting, because what's left is just simply algebra. So let's start. Identify x to the power r with the function g of x, 1 minus x to the power 1 minus r with the function h of x. By the chain rule, the derivative of the product g times h is g prime h plus gh prime, and those are the two terms on the right. G prime is the derivative of a power, and that we write down. H prime is the derivative of another power, and we write that down as well. And now we've got an expression involving products of powers. Right? The reader should pause, write this down, make sure she absorbs it. Once you've got that far, we'll just collect common terms. The power x to the power r minus 1 and the power 1 minus x to the power 1 minus r minus 1 as common from both sides. And then accumulate the remaining terms from each of the two terms inside the square brackets. Very good. Now, just go ahead and expand what is inside the square brackets. That's very simple. We write it out, and we find that the term rx cancels inside, leaving something very nice and simple in the square brackets. Now, let's take stock. In front of the square brackets on the right, we've got a term which is strictly positive, or at least is non-negative, as x varies between 0 and 1. So the only way, if x is not 0 or 1, for the derivative of the product to be 0 is that the thing in the square brackets is 0. And so if x is away from 0 or 1, you'll get 0 for the derivative if and only if x is equal to r. Now what about the end cases, x equal to 0 and x equal to 1? Then these cases are trivial, right? Because in this case you have a function which is anchored at 0. Right? You saw those functions going up like this. So they're anchored at 0, they're trivial cases. Those end cases don't give you maxima. So the maximum is going to be at an interior point, which is exactly at the point x equal to r. And therefore we conclude that the function f of x achieves its maximum when x is equal to r. R was s over n, and this leads to our conclusion that, in fact, the maximum likelihood estimate for your sample, estimating the unknown probability p, is exactly s over n.